The single greatest barrier to deep space is the weight of a water bottle. Our dreams of living among the stars have always been crushed by a simple, brutal fact. Everything we need to survive, from the air we breathe to the fuel that pushes our rockets, must be painfully hauled up from the bottom of Earth's deep gravity well. It is a tyranny of logistics that has kept us confined to brief, expensive visits. But what if the solution is already waiting for us, scattered across the solar system in frozen, silent abundance? The ultimate key to unlocking a permanent human future in space is not a new engine or a magical material. It is the ancient, simple substance of water ice, harvested from the moons and asteroids themselves. By the end of this, you will understand how this cosmic resource shatters the old rules of exploration and builds a new, sustainable path to the planets. How do we turn shadowed crater ice into the rocket fuel for a journey to Mars? What does it mean for humanity to stop being visitors and finally become inhabitants of the solar system? Are we ready to become a species that lives off the land, not just of Earth, but of the entire cosmos? That vibrant blue marble is an oasis of almost impossible rarity. For decades, we looked out at our neighboring worlds and saw only deserts of rock and vacuum, places that seemed utterly hostile to the chemistry of life as we know it. But our telescopes and our probes have slowly pulled back a veil, revealing a stunning truth. The solar system is not dry. It is dotted with frozen reservoirs, cosmic iceboxes holding the very ingredients we thought were Earth's exclusive privilege. To become a spacefaring civilization, we must first learn to read this new map. We must understand what this extraterrestrial ice actually is, and precisely where it has been hiding in plain sight. Let's start close to home with our own moon. For a long time, we thought it was bone dry, a place where the Apollo astronauts' footprints would lie untouched for millions of years in the absence of any weathering. But then we pointed our instruments at the poles. There, deep within craters whose floors have not seen direct sunlight for billions of years, temperatures plunged to some of the coldest in the entire solar system. In these permanent shadows, water molecules that arrived on comets or formed from solar wind interactions found a trap. They froze solid and have remained there, preserved in a state of eternal winter. This isn't a skating rink of pure ice, however. It's likely mixed intimately with the lunar soil, a frozen concrete we call regolith. But it is there, and it is accessible within just a few days' travel from Earth. Venture further out, and the reservoirs grow more profound. Mars has vast ice caps at its poles, visible from orbit, and we now know that significant water ice lies just beneath the surface across much of its mid-latitudes, sometimes mere centimeters down. Then look to the asteroid belt. The dwarf planet Ceres, a world once thought to be a simple rock, is now believed to be a kind of icy mudball, with a substantial portion of its mass likely being water ice beneath a dusty crust. But the true giants of water storage lie in the outer solar system. Jupiter's moon Europa is the classic example, an entire world encased in a cracked, global shell of ice, beneath which churns a salty ocean containing more liquid water than all of Earth's oceans combined. Similar subsurface oceans are suspected on moons like Ganymede and Saturn's Enceladus, which actively sprays its inner ocean's contents into space through magnificent geysers. This brings us to a crucial point. When we say extraterrestrial ice, we are rarely talking about a pristine, clear glacier like you'd find on Earth. This cosmic ice is often a complex, dirty mixture. It can be locked in a porous matrix of rock, creating something akin to a frozen sponge. It can be blended with other frozen volatiles, like carbon dioxide or methane, forming exotic ices that behave differently than pure water ice. It might be layered with dust and organic compounds. This isn't a complication, it's a clue. This mixture tells the story of the solar system's formation, a snapshot of the primordial ingredients that came together to build planets. But for our purposes, it defines the challenge. Extracting usable water from this frozen amalgam is not as simple as chipping a block from a glacier. It is a precise industrial process we must perfect in an alien environment. So this is our new map, no longer a chart of barren wastelands, but a guide to scattered oases. From the shadowed pits of our moon to the red plains of Mars, to the hidden oceans of distant moons, water is waiting. It is the universe's way of offering us a foothold. But to accept that offer, we must first learn how to unlock it from its frozen, ancient slumber. The next question becomes the most practical one imaginable. How on Earth, or rather, how not on Earth, do we actually go about mining it? The rocket equation is a law of physics that feels almost like a cosmic joke played on explorers. It states a simple, devastating truth. To lift a single kilogram of payload into orbit, you need many kilograms of propellant. But to lift that propellant, you need even more propellant to lift it. This creates a pyramid of fuel where each new layer you add at the bottom makes the entire stack heavier, demanding yet another layer beneath it. It is a tyranny of exponential growth. Think of it like planning a road trip where you must carry every single gallon of gasoline you will ever need from the moment you leave your driveway. Your car would be almost entirely fuel tank with barely any room for you, your luggage, or the supplies for the journey itself. This is precisely the trap that has confined human spaceflight. Every drop of water for an astronaut to drink, every molecule of oxygen to breathe, and every liter of fuel to adjust course or return home must be painstakingly and expensively launched from Earth. It makes missions staggeringly costly and limits their range and duration. We have been trying to explore the ocean while carrying all our water with us from the desert. Harvesting extraterrestrial ice shatters this entire paradigm. It moves the gas station from the desert to the coast. Water is not just for life support. Through a well-understood process called electrolysis, you can split it into its two core components, hydrogen and oxygen, which together form one of the most powerful chemical rocket propellants known. Imagine a spacecraft designed to go to Mars. Instead of launching from Earth with all the fuel needed for the entire round trip, it launches lean, carrying just enough to reach a depot in lunar orbit. That depot has been stocked with propellant produced from ice mined on the moon. The spacecraft refuels there, then journeys to Mars with a full tank. Upon arrival, it could potentially refuel again using resources from Mars itself for the return leg. Suddenly, the spacecraft is no longer a disposable, one-shot projectile. It becomes a reusable ferry shuttling between orbital way stations. The economics transform completely. The cost of getting to Mars is no longer about the brute force needed to escape Earth in one go, but about the sustainable operation of a new transportation network, one built on resources already waiting in the void. This is the first, most profound reason ice is the ultimate key. It breaks the rocket equation's cruel grip and rewrites the fundamental logistics of being an interplanetary species. But this transformation goes far beyond the fuel tanks of our rockets. It reaches into the very air we would breathe and the water we would drink. The second foundational reason extraterrestrial ice is our ultimate key is because water is the universal life support system. In the silent, radiation-bathed emptiness between worlds, every single resource is precious. Every drop of water, every breath of air must be accounted for, recycled, and guarded. For a mission to Mars lasting years, the math of carrying all the water for a crew is almost as daunting as the fuel problem. You are essentially asking a spacecraft to be a self-contained, miniature Earth for its entire journey, with no way to restock. This creates immense risk. A single leak or system failure in the life support loop could spell catastrophe. with no possibility of an emergency shipment from home. Harvested space ice changes this equation from one of precarious conservation to one of abundant renewal. Imagine a lunar base, its domes set against the stark black sky. Instead of a tiny, tightly monitored tank of water recycled again and again, the base taps into a local well, a deposit of ice mined from a nearby shadowed crater. That ice is purified and flows into the habitat. It provides drinking water. It nourishes hydroponic gardens where crops grow under artificial suns, providing fresh food and helping to regenerate the air. It is used for humidity control, keeping the living environment comfortable. And through that same process of electrolysis, it is split. The oxygen is fed directly into the habitat's atmosphere for the crew to breathe. The hydrogen can be used in fuel cells to generate power or combined with carbon dioxide from the crew's exhalations to potentially produce water and even methane through chemical processes, further closing the loop. This is the shift from an outpost to a homestead. A base supplied from Earth is a tent in the wilderness, utterly dependent on supply lines from a distant civilization. A base that can extract and process its own water from the ground is building a foundation. It is putting down roots. The psychological and practical impact is profound. It reduces the terrifying fragility of being so far from home. It turns a desperate struggle for survival into a manageable challenge of engineering and agriculture. This self-sufficiency is what makes long-term colonization more than just a dream. It is what could allow a community on Mars to not just survive, but to eventually thrive, to grow their own food, manufacture their own materials, and expand their habitat using local resources. They are no longer just visitors living out of a suitcase. They are inhabitants learning to live off the land of a new world, and it all begins with unlocking the water frozen in the soil beneath their feet. The chemistry that unlocks this future is elegantly simple, a basic science experiment transformed into a cosmic-scale industry. That harvested ice, once purified and melted, becomes liquid water. From there, we apply a fundamental process called electrolysis. By running an electrical current through the water, we can split each molecule apart, separating it into its two elemental building blocks, hydrogen and oxygen. These are not just gases. When combined back together in a rocket engine's combustion chamber, they ignite with a clean, intensely powerful fury, creating the most efficient chemical propellant combination we know. This is how we turn moon dust into starflight. But how do we build this chain of creation in an airless, barren landscape? The vision unfolds in a series of robotic steps. First, a specialized mining rover would venture into those permanently shadowed craters. Its job is not to dig massive pits, but to gently scrape or drill into the icy regolith, collecting that frozen soil mixture. This raw material is then transported to a mobile processing plant, likely stationed at the crater's sunlit rim. Here, using energy from vast solar arrays, the plant heats the collected material in a sealed chamber. The ice sublimates, turning directly from a solid into vapor, leaving the dust behind. That water vapor is then condensed, purified, and fed into the electrolysis system. The resulting hydrogen and oxygen gases are cryogenic, meaning they must be kept at incredibly low temperatures to remain liquid and dense enough for efficient storage. This is where the engineering becomes a true marvel. We must build tanks and depots that can hold these super-cold liquids for months or years in the alternating extreme heat and cold of space, with minimal loss from boiling off. One ideal location for such a depot is a Lagrange point, a gravitationally stable parking spot in space, like the one between the Earth and the Moon. A depot here becomes a strategic filling station, a gateway where spacecraft from Earth can rendezvous, refuel with locally produced propellant, and then depart for deeper destinations with full tanks. Consider the profound shift this enables. A mission to Mars no longer needs to launch from Earth as a single, monumental, and disposable object carrying all its fuel for the entire journey. Instead, a spacecraft launches lean, meeting a tanker in lunar orbit that is filled with fuel made from lunar ice. After refueling, it makes the journey to Mars with a robust propellant reserve. This changes everything. It means the spacecraft can be heavier, carrying more supplies or scientific equipment. It means the crew can have a larger, safer habitat for the long voyage. Most importantly, it means they can have a guaranteed return ticket, using fuel potentially manufactured on Mars itself from resources there. This repeatability is what transforms a one-time expedition into a sustainable transportation route. It is the foundational step for a true cislunar economy, where resources are gathered and processed in space, for use in space, enabling commerce between orbital stations, lunar bases, and eventually the planets. The rocket fuel flowing from these distant ice deposits becomes the lifeblood of an entirely new era of expansion. There is a silent, invisible storm raging through the void our ships must travel. Beyond the cold and the vacuum, space is flooded with radiation, a constant hail of high-energy particles from the sun and distant cosmic events. For astronauts on a multi-year journey to Mars, this radiation exposure is not a minor concern. It is one of the most significant threats to their health and the success of the mission. A spacecraft's hull can only stop so much, and adding thick, dedicated metal shielding from Earth runs straight back into the tyranny of the rocket equation, making the vessel impossibly heavy. But what if the very substance meant to sustain life on the journey could also be what protects it? This is where water ice reveals another of its hidden superpowers. Its molecular structure, rich in hydrogen atoms, is exceptionally effective at absorbing and scattering harmful radiation. Hydrogen is light, but it is dense at the atomic level, making it a perfect radiation shield. This transforms water from a simple consumable into a strategic building material. Imagine the walls of a Mars transit habitat. Instead of being lined solely with metal, they could have integrated tanks, layers of the ship's own water supply positioned to create a protective barrier for the crew quarters. In a more permanent lunar or Martian base, raw blocks of processed ice, perhaps mined locally and shaped into bricks, could even be used as a supplementary shielding layer for underground or surface habitats. This is the elegant, multi-purpose logic of living off the land. Every kilogram of water you source from space is a kilogram you did not have to launch, and it serves a dual role. It is the drinking water for tomorrow, the oxygen for next week's breath, the hydrogen for next month's fuel cell, and all the while, it is silently standing guard, absorbing radiation that would otherwise pass right through the walls. This synergy is what makes deep space habitation not just possible, but profoundly more practical. It moves us from a mindset of fragile endurance to one of resilient abundance, where the resources of our new environment become the tools for our own safeguarding. The staggering cost of reaching orbit is the locked gate before the open frontier. For all the progress made by reusable rockets, the price tag for every kilogram lifted beyond Earth's atmosphere remains the single greatest economic barrier to everything we wish to do in space. It is the bottleneck that constrains the size of our ambitions, the payloads of our science, and the business plans of our industries. Harvesting extraterrestrial ice proposes a radical economic escape route, one that moves the factory floor from the bottom of the gravity well to the destinations themselves. This is not merely about finding a resource, it is about restructuring the entire financial architecture of space exploration. The core of this shift is the concept of the orbital fuel depot. Today, a mission to Mars must be a single, monumental launch, a vessel carrying every ounce of propellant it will ever need from the moment it leaves the pad. This demands a colossal rocket, a perfect launch, and an astronomical price. But if that same spacecraft can launch with only a quarter of its fuel, rendezvous with a waiting depot in lunar orbit that is stocked with propellant made from lunar ice, and fill its tanks there, the equation shatters. Suddenly, the rocket needed to launch that spacecraft from Earth can be far smaller, far less complex, and exponentially cheaper. The heavy lifting, both literally and financially, is outsourced to the sustainable in-space infrastructure. This change in logistics unlocks a cascade of economic possibilities. It dramatically lowers the entry ticket for any entity wanting to send a mission beyond Earth orbit. National space agencies can plan more frequent, more ambitious journeys with their existing budgets. Private companies can design specialized spacecraft for mining, research, or tourism, knowing they can purchase fuel in orbit like a trucker buys diesel at a highway station. This fosters a competitive marketplace. Multiple companies might compete to provide the most reliable or cost-effective propellant delivery service to a depot. Others might innovate in mining rover technology or more efficient electrolysis systems to produce that fuel. This competition drives innovation downward, just as it has in the launch industry, ultimately reducing the cost of accessing space for everyone. It transforms space from a domain of singular, government-led flags and footprints into a true economic sphere, a place of commerce, industry, and open participation. The ultimate goal is a self-sustaining loop where the resources of space fund the expansion into space. Water ice is the first commodity, the foundational currency of this new economy. Once that currency is flowing, it pays for the next step, and the step after that, building a future where the cost per kilogram to orbit is no longer a barrier, but simply a line item in a much larger and far more promising ledger of interplanetary enterprise. Shackleton crater is a name that carries the weight of earthly exploration into the void. Near the moon's south pole, its floor lies in a darkness so deep and so permanent that it is one of the coldest places in our entire solar system. Within that profound chill, scientists believe, is exactly what we are searching for: water ice preserved for eons mixed into the soil. This is not a distant, abstract resource. It is a tangible target, a mere 3-day journey from our home planet. That proximity makes all the difference. Before we can become interplanetary miners, we must first become proficient lunar prospectors. The moon is not merely a destination for this new industry. It is the essential proving ground, the workshop where we will learn to turn cosmic ice into a usable resource. The lessons learned in its silent, airless craters will write the manual for everything that comes after. The first step is one of precise confirmation. While orbital data strongly suggests the presence of ice, we need ground truth. This is the role of a new generation of robotic scouts. Imagine a small, rugged rover descending into the eternal night of a crater like Shackleton. Its headlights would carve the first beams of artificial light into a darkness that has lasted for billions of years. This robot's mission is not yet to dig in earnest, but to sense. Using sophisticated instruments, it would map the precise distribution of the ice, determining its concentration, how deep it lies, and the nature of the soil holding it. Is it a thin frost-coating pebbles or a thick layer frozen solid several meters down? The rover might deploy a drill to bring up a core sample, a tiny cylinder of this frozen regolith that would be analyzed on the spot. This data is the foundation. It tells engineers exactly what kind of mining machine they need to build. Following the scouts come the pioneers, the experimental extraction systems. These are the prototypes of our future cosmic refineries. One concept involves a rover equipped with a large, enclosed bucket drum. It would drive slowly across the shadowed terrain, scooping up the icy soil. This material would then be transferred into a heated chamber on the rover itself. Inside, without ever exposing it to the vacuum, the ice would be gently warmed. It would turn from solid directly into vapor, a process called sublimation. That water vapor would then be piped away from the leftover dry soil, cooled, and condensed back into liquid water, or even frozen into a pure block. Another method might use a large parabolic mirror positioned on a sunlit crater rim, focusing sunlight into the shadowed area to provide the heat for this sublimation process. The goal of these early missions is not industrial output, but proof of principle. Can we reliably and repeatedly extract water from lunar soil with robotic systems, millions of miles from any human technician? Success in this endeavor does more than just produce a few liters of moon water. It validates an entire technological ecosystem. We prove that autonomous machines can operate for long periods in an extreme environment of crushing cold, fine dust, and low gravity. We learn how to handle materials that behave differently than they do on Earth. We test methods for storing volatile resources like liquid hydrogen and oxygen on the lunar surface. Each solved problem, each refined process, becomes a chapter in a new textbook, one titled How to Live Off the Land Beyond Earth. The Moon, with its short communication delay and relative accessibility, offers us a classroom where mistakes are survivable and lessons are immediate. A functional ice mining demonstration on the Moon is the keystone. It transforms the concept from a compelling theory on a whiteboard into a working, economic reality. It shows investors and the world that this is not science fiction, but the next logical step in our evolution as a spacefaring species. Once we can reliably produce a gallon of rocket fuel from lunar ice, the entire solar system begins to look different. It shifts from a map of distant destinations to a network of potential resources, all connected by the foundational technology first proven in the silent dark of a lunar crater. The Moon's shadowed craters are a perfect classroom, but the real treasure lies scattered on a cosmic scale. Beyond the orbit of Mars, in the vast expanse of the asteroid belt and even closer to home, drift ancient remnants from the dawn of the solar system, and many of them are not barren rocks. They are cosmic ice chests holding water and other volatile materials in staggering abundance. These asteroids, particularly a class known as carbonaceous chondrites, are time capsules. They are the leftover building blocks of planets, rich in the primordial ingredients that made our own world habitable, including vast quantities of water ice locked within their porous, dark structures. While the Moon offers a nearby testbed, these wandering mountains represent the next great frontier, the stepping stones that could allow us to build an infrastructure spanning the entire inner solar system. The challenge and the opportunity lie in their nature. An asteroid is a world without weight, a place of microgravity. This changes everything about how we would interact with it. You cannot simply land a mining rover on its surface as you would on the Moon, because a too forceful push could send you, or the entire asteroid, spinning off into a new trajectory. The very act of extraction becomes a delicate ballet of physics. One visionary concept to overcome this distance involves not going to the asteroid, but bringing a piece of the asteroid to us. The idea is to identify a small, water-rich near-Earth object, perhaps only the size of a house, and use a gentle, sustained thrust, like a solar electric propulsion tug, to nudge it into a stable orbit near Earth, perhaps around the Moon. This process, called asteroid redirection, transforms a distant resource into a local one, creating a fuel and material depot that is far more accessible than any object in the main belt. But then comes the intricate task of mining a world that is essentially a spinning pile of rubble, held together by the faintest whisper of gravity. How do you anchor to something that has no solid ground? Engineers envision systems that could envelop a portion of the asteroid in a flexible bag or deploy nets to contain loose material. Mining tools might not dig, but rather screw into the surface or use vibrations to stir the regolith, allowing the desired volatile ices to be drawn off through heating. Without strong gravity to help separate materials, we would rely on centrifugal force, spinning the asteroid or a collection chamber to fling heavier rock outward while capturing the lighter water vapor. Mastering these techniques unlocks a vision of almost limitless potential. A single water-rich asteroid could contain more accessible water than all the ice we might ever mine from the moon. This resource is not just for fuel. The other materials present, metals and silicates, could be processed in space to build everything from radiation shielding to entire space station components, without the crippling cost of launching them from Earth. This is the promise of the asteroidal frontier. It is the path from a single lunar outpost to a true solar system civilization, where the very materials for our expansion are harvested from the endless construction yard of space itself, turning distant rocks into the cornerstones of our future. Mars represents the ultimate test of our ability to live beyond our cradle. It is a world with a thin atmosphere punishing radiation, and a stark, beautiful desolation that calls to the explorer in us. But unlike the airless moon, Mars offers a profound and critical advantage for those who wish to stay. It holds its water ice not just in the deep freeze of polar caps, but scattered in accessible deposits across its very skin, a hidden aquifer waiting to be tapped. This isn't just about finding water, it's about finding a home. The location of this ice will literally map the future of human civilization on another world, dictating where we build our first enduring settlements. Imagine a base not placed solely for a beautiful view or scientific interest, but anchored directly over a buried glacier. The ground beneath the astronauts' feet isn't just regolith, it's a reservoir. This ice is the raw material for everything they will need to survive and one day to leave. The first and most immediate use is life support. That ice, once mined, melted, and purified, becomes a steady, reliable supply of drinking water. It nourishes hydroponic gardens where crops grow under artificial lights, recycling moisture and producing fresh food. Through electrolysis, just as on the moon, it is split into oxygen for the habitat's atmosphere and hydrogen for power. But Mars adds a spectacular twist to this chemical recipe, one that leverages its own unique environment. The Martian atmosphere is 95% carbon dioxide. This presents us with a remarkable opportunity through a chemical process called the Sabatier reaction. Here's how it works. We take the hydrogen derived from splitting Martian water ice and combine it with carbon dioxide scooped directly from the thin air outside. With the help of a catalyst and some heat, these ingredients react to produce two incredibly valuable products, methane and water. The methane is a powerful, storable rocket fuel. The water can be cycled right back into the life support system or split again to make more hydrogen, creating a beautiful, closed loop. This means a Martian base can manufacture the very fuel needed for spacecraft to return to Earth or travel across the planet, using little more than local water and air. It transforms the entire mission architecture. A crew arriving on Mars isn't stranded. They are the advanced team for a new branch of industry. Their first task is to deploy robotic miners and processing plants to begin stockpiling these resources, so that when the next crew arrives, there is fuel waiting for them, water already in the tanks, and oxygen in the habitat. This is the shift from a one-way trip to a sustainable cycle. It turns a daring expedition into the founding of a permanent outpost, one that can grow because it pays for its own expansion with the resources of its new world. The dream of a city on Mars begins not with a dome, but with a drill, reaching down into the frozen history of the red planet to unlock the future. But finding these cosmic oases is a task of extraordinary subtlety. You cannot mine what you cannot precisely locate and measure. Before a single drill bit spins or a heating chamber glows, we must become master cartographers of the invisible, learning to read the faint signatures of water hidden within alien landscapes. This first monumental technological hurdle is one of detection and mapping. Our eyes, even aided by the most powerful cameras, see only barren rock and dust. To find the ice, we must listen to the whispers of the atomic world. Orbiting spacecraft are our first scouts, equipped with instruments that see in spectra far beyond visible light. One of the most crucial tools is the neutron spectrometer. It works by detecting a telltale signature of hydrogen. As cosmic rays from deep space constantly bombard a planetary surface, they collide with atoms in the soil, sending neutrons flying back out into space. If those neutrons encounter hydrogen atoms, like those found in water molecules, they slow down dramatically. By measuring the energy of neutrons escaping into space, the spectrometer can map where hydrogen is concentrated. A pronounced dip in neutron energy reveals a hydrogen-rich zone, a strong indicator of water ice lurking below. Another indispensable eye in the sky is radar. By sending radio pulses down to the surface and timing their echo, scientists can peer beneath the top layer of dust. Different materials reflect radar signals in distinct ways. A layer of pure rock will scatter the signal, but a sheet of solid ice, buried perhaps a meter down, will create a sharp, bright reflection. This subsurface radar profiling allows us to create three-dimensional maps, showing not just where ice might be, but how deep it lies and how thick the deposit is. Yet these orbital maps, for all their sophistication, come with frustrating ambiguities. A hydrogen signature could indicate water ice, but it could also point to other hydrogen-bearing minerals, compounds that are bone dry. Radar might struggle to distinguish between solid ice and simply very porous, water-rich soil. This is the limit of remote sensing. We see the shadow of the resource, but not its exact hand. That final, critical step requires putting our instruments on the ground. This is called ground truthing, and it is the only way to turn a promising blip on an orbital map into a certified mining claim. It involves sending landers or rovers to the very spots our orbiters have flagged. These robotic geologists might use a miniature drill to bring up a core sample, heating it in an onboard oven to vaporize any ice and measure the water content directly. They might use ground-penetrating radar with a much finer resolution than any orbital instrument, or spectrometers that can analyze the chemical makeup of the soil in intimate detail. Each ground mission closes the loop, confirming what the orbital data suggested, and more importantly, revealing exactly what form the water takes. Is it a thin frost-coating grains of sand, or a solid block 3 meters down? Is it pure or mixed with ammonia or salts that would complicate processing? The answers to these questions write the first, indispensable page of the mining playbook. An accurate, high-resolution resource map is not just a scientific curiosity. It is the foundational business document for the entire enterprise. It tells engineers exactly what kind of machine to build, where to send it, and what yield to expect. It risks billions in investment and shapes the design of every mission that follows. Without this precise knowledge, we are digging in the dark. With it, we can place our first stake in the ground of a new world, confident that we are building on solid ice. But a map is only a promise. To fulfill it, we must move from observation to action, from finding the ice to physically wresting it from an environment designed to break our machines. The second great technological hurdle is extraction itself. Mining on Earth is a brutal exercise of force and endurance, but mining in the vacuum of space, at temperatures that plunge to 250 degrees below 0 Celsius, is a challenge of an entirely different order. Here, every familiar rule of engineering is rewritten by cold, dust, and a profound silence where nothing lubricates, nothing convects heat, and every moving part is at risk. The methods we devise must be as ingenious as they are robust, turning alien physics into an ally. One of the most straightforward concepts in principle is the heated drill or probe. Imagine a robotic apparatus that drives a heated tip into the frozen regolith. As it penetrates, the heat melts the ice around it, creating a slurry of water and soil. This mixture could then be pumped up to the surface through the hollow drill stem, where the water is separated from the grit. The elegance lies in its directness, but the complications are immense. That lunar or Martian soil, called regolith, is not like dirt on Earth. It is made of tiny, jagged glass shards, the product of eons of meteorite impacts pulverizing rock without air or water to soften the edges. It is profoundly abrasive, capable of grinding down seals and wearing through metal joints with shocking speed. Any system that moves this material must be designed for a world of eternal sandpaper. This leads to another family of concepts, the low-gravity excavators. On the Moon with 1/6 Earth's gravity, or on an asteroid with almost none, a traditional bulldozer would be a disaster. A heavy scoop digging into soil could simply lift the entire vehicle off the ground. Instead, miners envision machines that use their own weight strategically, perhaps anchoring themselves with screws or using very slow, deliberate motions to avoid bouncing. They might collect the icy regolith not to haul it far, but to transfer it immediately into a sealed processing unit right there on the mining site. This minimizes movement and the associated wear from that punishing dust. Perhaps the most elegant solution, however, bypasses moving heavy soil altogether. It is called thermal mining. This method exploits the unique physics of a vacuum. In the airless conditions of the Moon or an asteroid, when you apply heat to water ice, it doesn't melt into a liquid. It sublimates, transforming directly from a solid into a vapor. A thermal mining system would use focused sunlight, perhaps from a large mirror on a crater's sunlit rim, or simple electrical heaters, to gently warm a patch of icy ground. The ice deep within the soil would turn to vapor, and that water vapor would then migrate upward through the porous regolith. Above the patch, a large, cold dome or tent would be placed. The inside of this dome is kept extremely cold, so when the water vapor rises and touches it, it immediately refreezes as pure frost. Workers, or more likely robots, could then simply scrape this clean ice off the collector surface. The beauty of this method is its simplicity. It produces relatively pure water with minimal mechanical processing and very little moving parts exposed to the abrasive soil. The challenge is managing the heat, ensuring it penetrates deeply enough to liberate the ice without wasting vast amounts of energy heating worthless rock. No matter the method, these systems must operate with near total autonomy. The communication delay to the Moon is a few seconds, but to Mars it can be 20 minutes each way. You cannot joystick a complex mining operation with that kind of lag. Every robot, every processor, every drill must be smart enough to diagnose a jam, clear a blockage, or recalibrate its approach without a human in the loop. It must do this while enduring temperature swings of hundreds of degrees between sunlight and shadow. In a place where a loose cable doesn't just dangle, it can become a rigid, frozen serpent. The winning technology will not be the most powerful or the fastest in an earthly sense. It will be the one that maximizes water yield while minimizing energy use and mechanical complexity in this unforgiving workplace. It will be the system that turns extreme constraints into a design principle, creating a machine that is less like a terrestrial bulldozer and more like a patient, meticulous alchemist, using subtle heat and clever physics to coax water from a stone. The water you coax from the frozen ground of another world will not flow clear and pure. What emerges from a thermal collector or a heated drill is not a pristine mountain stream, but a complex alien slurry. It is a gritty mixture of water ice, razor-fine dust, and a cocktail of chemicals that have been frozen in time for billions of years. This raw material holds the promise of life and fuel, but it also carries potential poisons. The third monumental technological hurdle is the alchemy of purification, the silent, essential factory that must transform this cosmic ore into a safe, usable commodity. Think of it not as mining, but as refining. The goal is to take a dirty, unpredictable input and produce a perfectly consistent output, water so clean it can be split into breathable air and rocket fuel, or consumed directly by an astronaut without a second thought. The process begins with the first and most obvious contaminant, the dust. Lunar and Martian regolith is not like Earth soil. It is a fine, abrasive powder that gets everywhere and would quickly destroy pumps and clog filters. Initial separation might involve simple settling tanks, using centrifugal force in a spinning chamber to fling the heavier mineral particles to the outside while the less dense water or slush moves inward. From there, the water moves through a series of progressively finer filters, perhaps using ceramic membranes designed to withstand the harsh chemistry. But filtering only removes the solids. The invisible, dissolved contaminants are the greater concern. On Mars, and likely in some lunar deposits, the soil contains perchlorates. These are salts that are highly toxic to humans, damaging the thyroid and interfering with metabolism. They cannot be filtered out, they must be broken apart or removed chemically. One method is to run the water through a specialized resin bed that grabs onto the perchlorate ions, trapping them. Another approach could use advanced oxidation or biological processes employing engineered bacteria to digest the contaminants, turning them into harmless byproducts. For the most stubborn impurities, the final arbiter is distillation, a process perfected in the vacuum of space itself. By lowering the pressure inside a chamber, you can make water boil at room temperature. The water vapor rises, leaving nearly all contaminants behind, and is then condensed on a cold surface, producing water of exceptional purity. This multi-stage system, from coarse filtration to chemical scrubbing to vacuum distillation, must be a masterpiece of integrated, autonomous engineering. Every pump, every sensor, every valve represents mass that had to be launched from Earth at tremendous cost. Therefore, efficiency is not just desirable, it is mandatory. The system must have minimal moving parts to reduce failure points. It must recycle its own cleaning chemicals, and it must operate with very little energy waste. The purification plant becomes the heart of any off-world base, a piece of critical infrastructure that works continuously and reliably in the background. Its success is measured in silence, in the steady, uncontaminated flow of water that fills a habitat's tanks and feeds its electrolyzers. This stage completes the transformation, turning a raw planetary resource into the foundational currency of survival. It is the final, crucial step that assures us the water of other worlds will not just quench our thirst, but will safely sustain our future. Silent machines in a sunless crater cannot run on willpower alone. The entire enterprise of harvesting cosmic ice, from melting frozen soil to splitting water molecules, demands a torrent of reliable energy, a heartbeat for the industrial processes that would breathe life into dead worlds. This is the non-negotiable foundation, the energy imperative. Without a massive and steadfast power source, our robotic miners are just expensive statues, and our grand visions of fuel depots remain frozen on the drawing board. The most obvious candidate is the sun itself. In the airless clarity of space, solar energy is abundant, a constant flood of photons. Vast fields of photovoltaic panels could be deployed on the sunlit highlands of the moon, gathering power to be stored in batteries or transmitted to the mining operations below. But here we encounter the central paradox of lunar ice. The very deposits we seek, hidden in permanently shadowed craters, are by definition places where sunlight never, ever reaches. You cannot power a thermal mining operation in eternal night with solar panels placed in eternal day without overcoming immense logistical hurdles. Even on Mars, with its dusty atmosphere and longer nights, solar power becomes intermittent, requiring large-scale storage to survive the long, dark winters. For the heavy, continuous burden of industrial ice mining and processing, we need a source that does not sleep. This leads us to the most promising solution for these pioneering outposts: compact nuclear fission reactors. Unlike solar, a fission system provides a steady, dense stream of power regardless of the time of day or the depth of the crater. It is a plug-in heartbeat. Projects like NASA Killer Power are pioneering this very technology, aiming to create small, rugged reactors that can be safely launched from Earth and then deployed on another world. Imagine a unit roughly the size of a trash can, using passive heat pipes and Stirling engines to convert nuclear heat into several kilowatts of electricity for a decade or more. A cluster of these could power an entire mining outpost, running heaters, drills, electrolyzers, and life support systems around the clock. The development of such space-rated fission systems is not merely an engineering challenge. It is an enabling technology that makes every other step possible. Looking further ahead, more speculative concepts could revolutionize this landscape. Beamed power, for instance, where a solar station in permanent sunlight focuses microwaves or lasers to a receiver in the shadowed crater, could provide a wireless grid. And on the distant horizon, fusion reactors mimicking the power of the stars promise even greater energy density with fewer concerns about radioactive fuel. But for the first steps, fission represents the pragmatic, powerful choice. The critical insight is that the energy infrastructure built to support ice mining will never serve just that one purpose. The power lines or wireless transmission networks laid down to run a refinery become the backbone of an entire settlement. That same reactor humming away to produce rocket fuel can later supply electricity for habitats, greenhouses, scientific labs, and workshops for manufacturing tools from local materials. It transforms a single-purpose industrial site into the thriving heart of a new community. The first flicker of nuclear power on the Moon will do more than melt ice. It will ignite the chain reaction of permanent habitation, proving that we can generate our own sun in the darkness, and in doing so, light the way forward. The steady hum of a reactor and the silent flow of purified water will be orchestrated by a workforce that never sleeps, never breathes, and never looks back toward the blue marble of home. Human hands will guide this new frontier from a distance, but the gritty, dangerous labor of turning ice into opportunity will fall to armies of machines. This is not a single robot on a science mission. It is an entire robotic ecosystem, a symphony of specialized machines working in concert on an alien stage. Picture a prospecting rover, its wheels clawing through dust as dark as charcoal, mapping a shadowed crater with LiDAR and ground-penetrating radar. Its data feeds directly to a central hive mind, which dispatches a heavy mining vehicle to the richest vein. That miner, perhaps a tele-operated manipulator with the strength of an excavator and the precision of a surgeon, begins the extraction, its movements guided by a human operator watching through a screen back on Earth, but buffered by 20 minutes of light delay. Every scoop, every drill rotation must be planned with predictive algorithms, a slow-motion ballet where one wrong move could mean months of lost progress. Alongside it, an automated processing plant hums to life, receiving the raw, icy soil, running it through its purification cycles, and feeding the results into electrolysis stacks, all while monitoring its own health and signaling for maintenance. These machines talk to each other on a local network, a Wi-Fi web cast across an airless landscape. A prospector finds an anomaly, the system reroutes a miner, the plant adjusts its intake valves, all with minimal human intervention. This demands a leap in machine intelligence far beyond today's rovers. They will need computer vision that can distinguish a stable bedrock from a treacherous dust slope in the strange, high-contrast light of a crater rim. They will require machine learning that allows them to diagnose a clogged filter or a misaligned drill bit, and then attempt a pre-programmed fix. They must be resilient, capable of waiting out a dust storm or a communications blackout, and then picking up right where they left off. This is the birth of an entirely new industrial paradigm, one born not in a factory on Earth, but in the vacuum of space. It is the unsung workforce of the final frontier, building the infrastructure for humanity's arrival with silent, relentless efficiency. The silent machinery of a lunar refinery raises a profound question no robot can answer. Who owns the water it produces? This is not a matter of science but of law, a collision between our oldest dreams of exploration and the practical need for rules in a new frontier. The foundation of all space law is a document signed in 1967, the Outer Space Treaty. Its core principle is majestic and clear. Outer space is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. No nation can plant a flag on the moon or an asteroid and declare it theirs in the same way nations claimed continents on Earth. This treaty was born from the Cold War, a brilliant piece of diplomacy designed to keep the heavens a peaceful commons for all humanity. But it was written before anyone seriously contemplated a shovel of lunar soil having commercial value. It says nothing explicit about whether a private company can mine a resource, own that resource once extracted, and sell it. This legal silence created a vacuum, and nature abhors a vacuum. In 2015, the United States passed the Commercial Space Launch Competitiveness Act. This law made a crucial distinction. It affirmed that American citizens engaged in commercial recovery of space resources have the right to possess, own, transport, use, and sell those resources. Importantly, it states this does not constitute an assertion of sovereignty or ownership over the celestial body itself. Think of it like international waters. No nation owns the ocean, but a fishing vessel from any country has the right to catch fish from it and sell the catch. The U.S. law essentially says the same about asteroids and lunar ice. You cannot own the pond, but you can own the water you pull from it. Other nations, including Luxembourg and the United Arab Emirates, have followed with similar legislation, creating a patchwork of national laws for an inherently international domain. This is where the tension lies and where the urgent need for new frameworks emerges. Without clear, agreed-upon international rules, the stage is set for confusion and potential conflict. What happens if two companies from two different countries target the same small, water-rich asteroid? Who decides who mines which part of a crater on the moon? More critically, we need standards. What are the environmental protocols for mining on another world? How do we prevent contamination, both bringing Earth microbes to pristine environments and ensuring any potential extraterrestrial material does not harm Earth? How do we manage orbital debris created by increased traffic to and from these mining sites? The rules we write now are not just legal technicalities. They are the constitution for a solar system-wide civilization. They will determine whether this new frontier becomes a chaotic gold rush or an orderly, sustainable expansion. They will shape whether the benefits of space resources flow to a few or create opportunities for many nations. The goal is not to stifle innovation with bureaucracy, but to provide the certainty that allows massive, long-term investments to happen. Companies and governments need to know the rules of the road before they build interplanetary trucks. This is a monumental diplomatic challenge, requiring nations to look beyond terrestrial rivalries and think as a species embarking on a shared project. The process will be slow, contentious, and absolutely essential, for the promise of cosmic ice is not just in the water molecules themselves, but in the future we choose to build with them. The right legal frameworks can ensure that this new chapter of history lifts humanity together, turning celestial resources into a rising tide for all. This responsibility extends far beyond legal frameworks and into the realm of our conscience. With the power to harvest resources comes the profound duty to do so thoughtfully, to ask not just if we can, but if we should and how. We are on the cusp of becoming an interplanetary species, and the choices we make now will echo for millennia, setting a precedent for how we interact with every world we touch. This is the frontier of environmental ethics for our solar system, a necessary conversation we must have before the first industrial drill ever spins. Consider the Moon, that silent, ancient companion. Extracting ice from its permanently shadowed craters is a compelling goal, but those craters are also pristine scientific records. They are cold traps that have collected and preserved material from comets, the solar wind, and perhaps even the early Earth for billions of years. Mining operations, with their exhaust, vibrations, and potential for chemical spills, could irrevocably alter this fragile environment. We might gain the water we need, but lose an irreplaceable archive of our own solar system's history. The question becomes one of balance. Can we develop mining techniques that are minimally invasive, that leave large portions of these scientific sites untouched for future study? This isn't about stopping progress, it's about guiding it with wisdom, ensuring our expansionist drive walks hand in hand with scientific curiosity and planetary stewardship. The stakes grow exponentially higher when we look to worlds like Jupiter's moon Europa. Beneath its cracked, icy shell almost certainly lies a vast, global ocean of liquid water, warmed by the tidal forces of its giant planet. This makes it one of the most promising places in our solar system to look for life beyond Earth. The mere thought of sending a mining probe to Europa's surface should give us pause. Any spacecraft from Earth, no matter how carefully sterilized, carries with it a microscopic cargo of our own world's biology. A single, hardy microbe, surviving the journey and hitching a ride on a drill meant to sample the ice, could theoretically be carried into the subsurface ocean. This would be the ultimate contamination, a tragic case of finding life only after we had already introduced our own, forever blurring the line between discovery and pollution. It raises an ethical imperative as clear as it is challenging. We must develop and adhere to rigorous, updated protocols for planetary protection. These are the rules that govern how we clean our spacecraft, how we handle samples, and where we decide it is simply too risky to send our machinery until we have absolute certainty we can do no harm. This isn't just about preserving potential alien ecosystems, it's about preserving our own ability to learn. A contaminated Europa is a scientific opportunity lost forever. The principle of sustainable resource management must also travel with us. On Mars, water ice is a non-renewable resource on human timescales. If a future colony were to rapidly deplete a local glacier without thought for conservation or recycling, it could doom its own longevity. We must learn from the hard lessons of our history on Earth and build cycles of reuse and efficiency into the very blueprint of our off-world settlements. Developing these ethical frameworks is not a peripheral concern or a bureaucratic hurdle. It is central to the entire project of becoming a spacefaring civilization. It is about proving that we can grow not just as a technological species, but as a wise one. The ultimate key to deep space expansion isn't just the ice we find, but the careful, respectful hands with which we choose to gather it. A stable point in the void, a cosmic crossroads where gravity's pull finds a perfect balance. This is a Lagrange point, and it offers something priceless in the chaos of space, a fixed address. Here, at these gravitational way stations, we can build the first true ports of call for the solar system. Picture not a single spacecraft, but a bustling hub. A modular station where vessels from Earth, lunar mining outposts, and asteroid tugs can all rendezvous. This is the fuel depot, the gateway concept brought to life by the steady flow of propellant harvested from cosmic ice. Its primary cargo is the lifeblood of exploration, liquid hydrogen and oxygen, chilled to cryogenic temperatures and stored in vast, insulated tanks. But a depot is far more than just a floating gas station. It is an interplanetary port, complete with standardized docking interfaces, repair bays, and communications relays. Any spacecraft designed to use its services would have a common fuel port, much like cars today use a standard nozzle at any gas station. This standardization is revolutionary. It means a ship launched by a national space agency, a private research group, or a commercial transport company can all pull into the same port, refuel from the same tanks, and be on their way. It transforms spaceflight from a series of one-off, custom-built missions into a modular, flexible system. Imagine planning a mission to Mars. Instead of designing a single, monstrous vessel that must carry everything for the entire journey from Earth's surface, engineers can now think in modules. A lightweight crew capsule launches from Earth with just enough fuel to reach the depot. A separate, reusable habitat module, perhaps already waiting at the depot after a previous mission, docks with it. Both are fueled from the depot's reserves, and the combined ship departs for Mars with a full tank, optimized for the long voyage. This architecture slashes risk. If a component fails, it can be replaced at the depot without dooming the entire mission. It increases flexibility, allowing missions to be assembled, reconfigured, or redirected based on new goals or opportunities. For the private sector, this is the infrastructure that makes business possible. A company focused on asteroid mining doesn't need to build a spacecraft capable of the round trip all the way back to Earth's atmosphere. It needs only to get its harvested water to the nearest depot, where it can be processed and sold as propellant to any passing customer. The depot becomes a marketplace, a neutral trading post that fuels the entire cislunar economy and beyond. This network of way stations, supplied by the ice of the Moon and asteroids, forms the foundational skeleton for all future deep space travel. It is the practical realization of a dream where the solar system stops being a collection of distant, isolated destinations and becomes a connected neighborhood, with open ports enabling the constant, sustainable flow of ships, people, and promise. The relentless drive to solve a problem in space rarely leaves the Earth untouched. Every bolt tightened, every line of code written for a robot miner on the Moon, carries the potential to spin off into a technology that transforms lives back on our own planet. The extreme constraints of space, that unforgiving environment of vacuum, radiation, and brutal cold, act as a forge for innovation. Engineers cannot simply make things bigger, heavier, or more power-hungry. They must invent systems that are supremely efficient, incredibly reliable, and able to operate with near-total independence. This pressure to innovate for survival beyond our atmosphere creates a cascade of solutions with profound applications right here at home. The technological journey to harvest cosmic ice could yield breakthroughs that address some of our most pressing terrestrial challenges. Consider the autonomous robots destined for those shadowed lunar craters. To operate for years with minimal human oversight, they will need an unprecedented level of machine intelligence and physical resilience. They must navigate treacherous, unknown terrain, diagnose their own mechanical problems, and perform complex tasks like drilling or sample handling without a real-time controller. The software and hardware developed for this purpose could revolutionize dangerous jobs on Earth. Imagine autonomous mining robots descending into unstable tunnels after a collapse, searching for survivors where it is too risky for human responders. Picture similar machines deployed into the radioactive wreckage of a disaster zone, carefully clearing debris or assessing structural damage. The precise, durable manipulator arms designed to handle abrasive lunar soil could be adapted for deep-sea construction or repairing critical infrastructure in hazardous environments. The challenge of mining ice in space directly fuels the advancement of robotics that make hazardous terrestrial work safer and more effective. Then there is the alchemy of purification. The systems designed to turn dirty, chemical-laced lunar or Martian ice into perfectly pure water must be miracles of compact efficiency. They have to remove not just fine dust, but toxic compounds like perchlorates, using minimal energy and with components that almost never fail. The technologies perfected for this, whether advanced ceramic filters, novel chemical scrubbers, or ultra-efficient vacuum distillation units, could be scaled and adapted for use in arid regions or communities with contaminated water supplies. A portable, solar-powered version of a space-rated water purifier could provide clean drinking water from brackish wells or polluted sources, operating for years with little maintenance. The fight to make alien ice drinkable could lead to a new generation of life-saving water technology for millions on Earth. The energy imperative for these off-world outposts pushes the boundaries of power generation. Compact fission reactors like those envisioned for lunar bases are designed to be safe, self-regulating, and able to produce steady electricity for a decade or more from a relatively small fuel load. While terrestrial nuclear power is well established, the miniaturized, ultra-secure designs required for space could lead to new classes of microreactors. These units could provide reliable, carbon-free power for remote communities far from the electrical grid, for disaster relief operations, or for forward operating bases where traditional fuel supply lines are vulnerable. The need to power a factory on the Moon accelerates the development of dense, portable energy sources that could help decarbonize and stabilize power networks in the most challenging locations on our own world. This is the often overlooked return on investment for becoming a spacefaring species. The monumental effort to harvest resources beyond Earth does not exist in a vacuum. It forces us to rethink fundamental engineering principles to build better, smarter, and more sustainably. Each solution forged in the crucible of space carries a blueprint for application back home. The pursuit of cosmic ice is not just about reaching outward, it is about creating a feedback loop of innovation. The technologies we develop to live among the stars have a powerful, proven history of circling back, improving life on Earth in unexpected and vital ways, turning the challenges of the final frontier into gifts for our first and most precious home. The clock is already ticking on this new industrial age. A realistic roadmap for harvesting cosmic ice stretches across decades, a patient campaign of incremental steps where each success unlocks the funding and confidence for the next, far more ambitious phase. We are not waiting for a single magic moment, but building a ladder to the stars, one rung at a time. The current decade, the 2020s, is the era of the Robotic Prospector. Right now, multiple missions from various nations are taking aim at the lunar South Pole. Their goal not to return samples for a museum, but to map and measure the ice itself with ground truth precision. These are the scouts, the surveyors staking out the first claims in this new frontier. Their data will answer the critical questions of concentration, depth, and accessibility, turning orbital hints into a definitive mining prospectus. Alongside them, small-scale technology demonstrators will test key components, perhaps a drill that can operate in deep cryogenic cold or a compact system for extracting water vapor from simulated regolith in a vacuum chamber on the lunar surface. The goal of this decade is not to produce industrial quantities of water, but to retire the biggest technical risks and prove the fundamental principles are sound. Success here transforms the entire endeavor from speculative theory into a credible engineering challenge. The following decade, the 2030s, is where we move from prospecting to pilot production. Building on the knowledge gained, the next wave of missions will deploy integrated systems, small pilot plants designed to operate for months or years. These will not be massive refineries, but the functional prototypes that demonstrate the complete chain, from excavation to purification to storage. Their output might be measured in kilograms, not tons, but it will be real, usable water and oxygen produced on another world. This is the crucial demonstration of economic viability. This pilot production could directly support a sustained human presence in lunar orbit, such as the planned Gateway Station, by providing a demonstrable local source of consumables. It proves the logistics chain works, that resources mined in one location can fuel operations in another, creating the first in-space economic loop. The confidence built here is what attracts serious commercial investment, moving the project from government-led science to a burgeoning industry. By the 2040s, the tempo accelerates from demonstration to operational scale. On the Moon, what began as a pilot plant could evolve into a continuously operating facility, producing propellant not just for its own support, but for sale to other lunar ventures or for fueling tugs bound for the Earth-Moon Lagrange points. This is when the first commercial fuel depots become a practical reality, enabling entirely new mission architectures. It is also the likely era for the first dedicated missions to water-rich near-Earth asteroids, leveraging the now mature technologies of autonomous operation and resource processing in microgravity. These would be the Pathfinder missions for true asteroidal mining, perhaps aiming to redirect a small, suitable object into a stable orbit for detailed assessment and extraction. Concurrently, on Mars, the foundational infrastructure for long-term habitation would be taking shape, heavily reliant on robotic precursors that have spent years stockpiling water and producing fuel from the Martian environment in anticipation of human arrival. Each of these steps is monumental, yet each is built directly upon the lessons and technologies of the stage before it. This phased timeline underscores a vital truth. The harvest of extraterrestrial ice is not a single invention we are waiting for, but a complex ecosystem of technologies we are actively constructing. It is a symphony of robotics, energy systems, chemistry, and law, each section needing to learn its part before the whole can perform. The journey from a robotic drill biting into shadowed lunar soil to a bustling interplanetary economy is measured in human perseverance as much as in astronomical units. It is a testament to our species' unique capacity to plant seeds for a forest we ourselves may never sit beneath, trusting that the shade and the oxygen it produces will be the inheritance of generations to come. The ultimate key is not just in the ice, but in our willingness to follow this long arc, to invest in a future that patiently, inexorably unlocks the solar system. The shadowed craters of the Moon hold no allegiance to any flag planted upon them. As the technical and legal frameworks take shape, a more human question emerges from the silence. Will the harvest of cosmic ice become a story of our species uniting around a shared frontier, or will it replay the old, terrestrial dramas of competition and rivalry on a grand celestial stage? The potential for both paths is already written into the early plans of nations and corporations, setting the stage for a defining chapter in our history. On one hand, the landscape resembles a new kind of gold rush. Multiple national space agencies have formally announced missions targeting the lunar South Pole, a region rich in suspected ice deposits. Private companies, fueled by national legislation that grants them rights to extracted resources, are designing their own landers and rovers with mining in mind. The risk is a congested, uncoordinated scramble for the most accessible and lucrative sites. Without clear rules of the road, this could lead to disputes over interference, claims of priority, or even the creation of hazardous debris from too many vehicles operating in a tight area. The specter of a zero-sum game in space, where one entity's gain is seen as another's loss, could inject terrestrial tensions into the void, slowing progress and increasing costs for everyone as nations and companies build redundant, competing infrastructures from scratch. Yet, the very magnitude of the challenge whispers a compelling argument for the opposite approach. The costs are astronomical, the risks are profound, and the technical hurdles are monumental. No single nation or company possesses all the capital, all the expertise, or all the political will to establish a permanent, sustainable presence alone. This reality naturally pushes toward collaboration, toward sharing the burden to achieve a goal that benefits all of humanity. We have a powerful blueprint for this in the International Space Station, a project that survived shifting political winds because its value as a shared outpost outweighed national differences. An expanded version of such a framework for lunar or asteroidal development is not just idealistic, it is pragmatic. Imagine an international consortium agreeing to fund and build a shared propellant depot in lunar orbit. Any member nation or approved private entity could use it, paying fees that fund its maintenance and expansion. Shared communication networks, standardized docking ports, and cooperative robotic fleets for prospecting could dramatically reduce costs and increase safety for every participant. This collaborative path does more than save money, it builds trust. It creates a web of mutual dependency and shared success in an environment where isolation is a profound vulnerability. A stranded crew is a tragedy for all humanity, not just their nation of origin, and a robust, cooperative infrastructure makes rescue and support far more likely. The path we choose now, in these formative years, will cast a long shadow. A competitive race might accelerate certain technologies in the short term, driven by rivalry, but it could also litter the strategic zones of space with proprietary systems that cannot communicate, leading to inefficiency and potential conflict. A collaborative framework might require more patient diplomacy and compromise, but it would likely lead to a safer, more stable, and ultimately more prosperous expansion, where the infrastructure built becomes a rising tide that lifts all ships. The water ice itself is neutral, merely a resource. The true test is whether we can develop the wisdom to gather it in a way that brings our species together, using the resources of the cosmos not as prizes to be won, but as a common foundation upon which to build a future for everyone. This transformation reaches far deeper than any fuel tank or life support system. The moment we drink water mined from lunar soil or breathe oxygen cracked from Martian ice, something fundamental changes within us. We are no longer just visitors camping in a hostile land, terrified of a supply line snapping millions of miles away. We become inhabitants. This is the quiet, psychological revolution at the heart of the entire endeavor, a shift in identity that may ultimately matter more than any piece of machinery. For all of human history, exploration has followed a familiar rhythm. We venture out from a place of safety, carrying our world with us in our packs and ships. We are guests in a wilderness, and our stay is temporary by design. This is the visitor mindset. It is cautious, constrained, and defined by scarcity. Every resource is counted, every contingency is a potential death sentence. It is how we have operated in space since the beginning, and it has kept us alive, but it has also kept us confined. Harvesting extraterrestrial resources shatters that old rhythm. When you can tap a local well, when you can manufacture the air you breathe from the ground beneath your feet, the relationship with your environment undergoes a radical rewrite. The base is no longer just a base, a collection of modules where you endure until the ride home. It starts to become a home. You are not just surviving the land, you are learning from it, working with it, drawing sustenance from it. This fosters a different mentality entirely, one of stewardship and long-term investment. You begin to think in terms of seasons, of cycles, of permanence. Why would you trash the local environment if your grandchildren might depend on its delicate balance? Why would you waste a single drop of water if it is the lifeblood of your community, pumped from the aquifer that sustains you? This is the inhabitant mindset. It is rooted in resilience, responsibility, and a profound sense of place. It is the difference between a tourist in a hotel and a farmer tending an orchard they planted themselves. One is passing through, the other is putting down roots, thinking in decades, not mission durations. This shift redefines what it means to be a spacefaring species. It moves us from being a civilization that occasionally visits space to one that genuinely lives there, with all the cultural richness and complex identity that entails. The children born in a habitat on Mars will not see Earth as home in the same visceral way we do. Their home will be the red plains outside their viewport, the recycled water in their taps, the community they build. They will be Martians, and with that new identity comes a new kind of wonder, not just the wonder of visitors seeing a strange sight, but the deeper wonder of inhabitants understanding their world, nurturing it, and watching their legacy grow within it. That psychological leap from packing a suitcase to planting a garden is perhaps the ultimate key the ice unlocks. It is the moment we stop being guests in the cosmos and finally become its residents. But the story does not end with water. That frozen deposit is not a single resource, but a complex chemical library, holding other volatile compounds locked away in the same deep cold. Ammonia, methane, carbon dioxide, they are often frozen right alongside the water molecules, a mixed bounty delivered by ancient comets and preserved in the same icy vaults. If water is the key to survival, these other volatiles are the keys to thriving, to building not just an outpost but a true industrial base. Each one unlocks a different door in the chain of self-sufficiency. Take ammonia. On Earth, it is a crucial component of fertilizer, and in the sterile environment of space, it could play the same vital role. Combined with water and minerals, ammonia could nourish the hydroponic gardens that feed a settlement, turning a closed-loop life support system into a more robust, more productive agricultural endeavor. Methane, often found frozen on distant moons or produced from local resources as we discussed with Mars, is more than just rocket fuel. It is a fundamental building block for organic chemistry. With the right processes, methane can be transformed into plastics, polymers, and synthetic materials. Everything from flexible tubing for habitat repairs to durable tools manufactured on site, reducing the need to ship every spare part from Earth. Even carbon dioxide, scooped from the Martian atmosphere or released from icy deposits, is a versatile feedstock. Beyond being converted into oxygen and methane, it can be used in greenhouses to supercharge plant growth or processed into carbon fibers, creating strong, lightweight materials for construction. This transforms the mission of an ice mining operation. It is no longer a single-purpose water pump. It becomes the heart of a broader chemical refinery, a facility that takes in raw, frozen cosmic material and outputs a portfolio of products essential for a permanent presence. The process of accessing this ice yields a second, equally valuable prize. To reach the frozen layers, you must first move the dry topsoil, the regolith. This material, often seen as waste in the quest for water, is itself a treasure. Lunar and Martian regolith is rich in metals like iron, aluminum, and titanium, as well as silicon and oxygen bound up in minerals. Once you have the energy infrastructure and processing plant in place for the ice, you can turn that same industrial capacity toward the rock. That regolith can be sintered with focused sunlight or microwaves to create solid bricks for landing pads and radiation shielding. It can be processed through more advanced methods to extract pure metals for manufacturing machinery or oxygen for breathable air. So the simple act of digging for ice does double duty. It provides the life-giving water and propellant, and it simultaneously uncovers the very building blocks of civilization. An ice mining site naturally evolves into the first true industrial park off Earth. It is the anchor point for what scientists call in-situ resource utilization, a term that simply means living off the land. This is the full vision, where one resource stream feeds another in an expanding cycle of capability. The water enables the power and the life support. The power enables the mining and refining of both ice and rock. The refined materials enable construction, manufacturing, and agriculture. What begins as a robotic drill in a dark crater blossoms into a self-sustaining ecosystem of production, where the local environment supplies nearly everything needed to grow, repair, and prosper. This is how a foothold becomes a home. Such power over a fundamental resource inevitably leads to a breathtaking question. What if we could use this mastery not just to visit worlds, but to remake them? Looking centuries into the future, the ability to locate, harvest, and transport cosmic ice could evolve into something far grander than supporting outposts. It could become the foundational tool for the most ambitious project imaginable, the deliberate engineering of an entire planetary environment, a process we call terraforming. The most compelling candidate for such an endeavor has always been Mars, a world with a tantalizing past of flowing water and a thin, cold present. The vision is audacious. To make Mars more Earth-like, we would need to thicken its atmosphere to retain heat, raise the surface pressure, and ultimately reintroduce liquid water to its barren valleys. A crucial ingredient for all of this is hydrogen, the very element locked in water ice. The scale required is almost beyond comprehension, requiring not just the ice buried on Mars itself, but a massive influx from elsewhere. This is where the long-term vision of an ice trade emerges. Imagine identifying water-rich comets from the distant Kuiper belt or icy asteroids from the outer solar system. Using the same principles of propulsion and navigation we are developing today, but on a vastly more powerful scale, we could nudge these frozen mountains onto new trajectories, guiding them slowly over decades or centuries on a collision course with Mars. The impact itself would be carefully calculated. Rather than a cataclysmic event, the goal would be a controlled delivery. The comet would be broken apart in the upper atmosphere, its immense payload of water ice vaporizing and dispersing. This would accomplish several transformative goals at once. It would release vast quantities of water vapor and other gases, directly thickening the Martian atmosphere. The added greenhouse gases would begin trapping more of the sun's feeble heat, initiating a warming trend. Over time, as temperatures rose, the remaining water ice on the surface and delivered by these impacts could melt, forming persistent bodies of water, the first seas on Mars in billions of years. This is not a quick process. It is the work of millennia, a multi-generational project undertaken with patience we can scarcely grasp today. To support such an endeavor, a more routine commerce would likely arise first. Specialized spacecraft, true ice freighters, could establish regular routes. They might harvest clean, pure ice from the rings of Saturn or the frozen surfaces of distant moons, transporting it as a precious commodity to dry inner system colonies or construction sites in orbit. This interplanetary trade in water would be the lifeblood of a truly solar system-wide civilization, where resources flow to where they are most needed, not just where they were originally found. While these concepts dwell firmly in the realm of far future speculation, they serve a vital purpose today. They illustrate the ultimate horizon of the path we are now starting down. The technology to mine a patch of lunar ice is the embryonic form of the technology needed to redirect a comet. The logistics of storing and transporting cryogenic propellant are the early lessons for managing an ice freighter's cargo. This progression redefines humanity's potential role in the cosmos. We begin as scavengers, learning to use what we find. We become builders, creating infrastructure from local materials. And finally, we might one day become gardeners on a planetary scale, using our understanding of chemistry and orbital mechanics to nurture dormant worlds back to life. It is a responsibility of almost sacred magnitude, reminding us that the key we are forging today opens doors to futures we are only beginning to dare envision. Such a future rests on solving problems that seem insurmountable today. The sheer scale of investment required to build the first off-world ice mine is staggering, a figure that gives even the most optimistic planner pause. Critics rightly ask, why pour such vast sums into a distant, frozen desert when pressing needs exist right here on our own planet? The robotics needed are unlike anything we have ever built, expected to operate flawlessly for years in a place where a single jammed gear could mean mission failure, with no mechanic within a million miles. And our orbital maps, for all their sophistication, are still just educated guesses. What if we land a billion-dollar excavator only to find the ice is a thin, useless frost, or locked in rock so hard it breaks our drills? These are not frivolous doubts, they are essential engineering questions that must be answered before a single dollar is spent on an industrial scale. The response to these challenges is not blind optimism, but a deliberate, phased strategy designed to retire risk one step at a time, transforming monumental leaps into a series of manageable steps. The first phase is not about profit but about proof. Small, focused robotic missions like the prospectors heading to the lunar poles now have a single job: to confirm what we think we know. Their price tag is a fraction of a full mining operation, and their success or failure provides priceless data. Finding that a particular crater has poor ice concentration is not a failure, it is a saved fortune, steering the next mission to a better site. Following confirmation, the next phase involves compact, integrated demonstrators. Think of them not as factories, but as breadboard prototypes in the environment itself. A lander that can drill 1 meter, heat a few kilograms of soil, and capture the resulting vapor would be a monumental success, proving the core extraction chain works in the real environment. These demonstrators are designed to be low cost and resilient, expecting things to go wrong so we can learn how to fix them. This iterative testing is how confidence is built, not in boardrooms but in the hard vacuum of space. It de-risks the technology, showing investors and the public that the fundamental physics and engineering are sound. This is where government agencies play an indispensable role. Their mandate extends beyond quarterly profits to advancing foundational knowledge and capabilities for the long-term security and economic vitality of the nation. By funding these high-risk, high-reward early demonstrations, governments can build the technological track record and regulatory frameworks that create a stable environment for private investment. Once a pilot plant on the Moon produces its first liter of certified rocket propellant, the equation changes. The risk profile shifts from "can it be done" to "how efficiently can it be done?" Private capital, which naturally seeks return but avoids pure speculation, can then enter with clearer models, investing in scaling up a proven process rather than betting on a miracle. This partnership between public pioneering and private optimization is a model with a proven history, from the development of the Internet to the modern commercial launch industry. Acknowledging the skeptics is not conceding defeat. It is the first and most necessary step in any serious engineering endeavor. It forces rigor, demands better designs, and ensures that the path we chart is not a fragile line over a chasm, but a solid bridge built pier by pier, tested at every stage. The dream of living off the land of other worlds is too important to be left to dreams alone. It must be engineered, and true engineering begins by listening carefully to every doubt and methodically designing an answer. The blueprint for this future is being drafted in real time, on screens and in labs around our planet. This grand narrative of harvesting cosmic ice and building a civilization among the stars is not a spectator sport reserved for a select few. It is a collective human project, and its success hinges not just on the brilliance of engineers, but on the engagement and support of a global public. You have a role in this journey, a chance to be more than just a witness to history. You can be a participant in the new space age, and your involvement can take many meaningful forms. Start by becoming an informed observer. The missions that will map the first ice deposits and test the first extraction technologies are not secret. Follow the public channels of the space agencies leading the charge, like NASA and the European Space Agency. Watch the live streams of private companies like SpaceX and Blue Origin as they test the rockets and landers that will carry this new industry. When a robotic prospector touches down in a lunar shadow, you can watch it happen. This awareness does something powerful. It builds a shared cultural context, a common understanding that this is happening now, turning the abstract concept of space resources into a series of tangible events we all experience together. That cultural momentum is vital because it translates into tangible support. Space exploration, especially the foundational, high-risk work of proving new technologies, requires sustained investment. You can advocate for that funding by understanding its value and communicating it to others. This isn't about choosing space over solving Earth's problems. It is about recognizing that the technological surge required to live on the Moon directly spins off innovations in medicine, computing, materials science, and environmental management that benefit life on Earth. Supporting a robust and forward-looking space program is an investment in our species' long-term resilience and ingenuity. Perhaps the most direct impact you can have is by nurturing the next generation of problem solvers. Support STEM education in your community. Encourage curiosity about robotics, planetary geology, chemistry, and even the emerging field of space law. The challenges of mining ice in a vacuum will not be solved by a single genius, but by diverse teams of specialists working in concert. A child fascinated by coding today might write the autonomous navigation software for a Martian ice miner tomorrow. A student passionate about environmental science could develop the closed-loop life support systems for a lunar base. By fostering these interests, you help build the human capital that will turn these blueprints into reality. For those looking at their own career path, the horizon has never been broader. The space industry is expanding beyond astronaut and rocket scientist to include a vast array of essential roles. We will need roboticists to design and maintain the autonomous miners, geologists and chemists to analyze extraterrestrial soils and develop purification processes, lawyers and policy experts to craft the fair international frameworks that will govern this new frontier, engineers specializing in power systems, cryogenics, and in-situ manufacturing. Even artists and storytellers will be crucial, helping humanity process and envision this profound shift in our place in the cosmos. Your unique skills, whatever they may be, could find a vital application in this expanding ecosystem. Ultimately, every informed conversation, every shared article about a new mission, every student you encourage, adds to the gravitational pull of this future. It creates a society that expects and supports exploration, that views the solar system as our next chapter rather than a distant backdrop. This collective will is the fuel for the long journey ahead. The future of space is not a pre-written book we are waiting to receive. It is a story being drafted now in mission control rooms, in university labs, in legislative hearings, and in living rooms around the world. Everyone, including you, holds a pen. The question is not whether you will watch this story unfold, but what line you will help write. The silent architect of our future has been waiting in the dark all along. From the shadowed craters of our moon to the frozen plains of Mars, water ice is not merely a resource, it is the blueprint for a new kind of civilization. Our journey through this idea has shown us a profound transformation. We have seen how this cosmic ice solves the most fundamental problems, breaking the cruel mathematics of the rocket equation by becoming the fuel that propels us onward. It provides the very water and air for life support, shifting our mindset from desperate conservation to one of sustainable abundance. It even serves as a shield, protecting us from the invisible radiation storms of deep space. This single substance rewrites the entire economic model of spaceflight, turning impossibly expensive one-way trips into the affordable, repeatable routes of a true interplanetary transportation network. Yet this path is not a simple one. We have confronted the immense technological hurdles, from building robots that can mine in perpetual darkness to creating purification systems that turn alien slurry into pristine water. We have grappled with the ethical questions, understanding that with the power to harvest comes the profound responsibility to do so wisely, to protect the scientific sanctuaries of other worlds, and to build frameworks for peaceful cooperation. This endeavor demands more than engineering brilliance. It calls for wisdom, for foresight, and for a commitment to collaboration that rises above old rivalries. Harvesting extraterrestrial ice is far more than an advanced mining technique. It is the master key. It unlocks a future where humanity is no longer confined to its birthplace, but becomes a sustainable, expansive, and permanent presence throughout the solar system. The universe, in its ancient generosity, has scattered the resources we need right across our celestial neighborhood. They are there in the frozen dark and the dusty plains. The next great chapter of our history is not preordained. It awaits our choice, our effort, and our courage to reach out and grasp it. It is a chapter that will be written not on paper, but in water among the silent, watching stars.